Hey everyone, and welcome to this explainer. Today, we're tackling what is honestly one of the biggest hurdles in Cambridge AS and A-level physics. We are talking about how tiny, completely invisible microscopic changes totally dictate the macroscopic world we see every single day. If you really want to ace the 9702 exams, you can't just memorize a list of formulas and hope for the best. You've got to understand this bridge between the small and the large. So let's break it down step by step.
Right, let's kick things off with a classic trap. This one quietly costs 9 out of 10 students their top grade. Is an insulator just a conductor that failed? Well, in the middle of an exam panic, it's super tempting to just write down that an insulator is simply a material that blocks or, fails to conduct electricity. Makes sense, right? But here's the thing. Examiners absolutely do not care about what a material doesn't do. They want to know what it actually does. Take a look at the massive difference between a generic answer and a high-scoring one. On one side, we've got the scattered facts, calling it a broken or failed conductor. Honestly, that's a dead end. On the other side, we have that high-mark logic. Examiners really want to see you treat a dielectric, which is an insulating solid, as an active participant. It dynamically responds to an electric field through a pretty amazing invisible process called internal polarization. And here is the exact definition you need to absolutely lock in for test day. Polarization is definitely not about a free-flowing current. In a dielectric, the charges are completely trapped. They can't just move around freely. Instead, when you apply an external field, it's kind of like a microscopic tug of war. The bound positive and negative charges stretch and shift just a tiny bit away from their center. There's zero large-scale current going on here, just a very subtle internal shift. To guarantee those high marks, you need a foolproof framework. Think of it like a 4-step chain reaction. Step 1, the external field is applied. Step 2, that microscopic internal shift of bound charges kicks in. Step 3, this creates a net polarization across the entire material. And finally, step 4, the macroscopic result, the altered electrical behavior that we can actually observe. If you string these 4 steps together, you've perfectly explained the why behind the physics. Now, this micro-to-macro framework, it isn't just for electricity. It literally unlocks the whole syllabus. Take equilibrium position and restoring forces. When an atom gets bumped out of its normal position, internal spring-like microscopic forces immediately pull it right back. And that tiny, invisible atomic vibration, that is the exact mechanism driving macroscopic heat transfer in things like overheating microchips. The internal, invisible physics is always what creates the external, visible reality. And guess what? This exact same logic applies straight to magnetism too. Rather than just dropping a super vague term like magnetic field on your exam paper, build that chain. The microscopic mechanism here is the orbital motion and intrinsic spin of electrons. When these tiny atomic behaviors align, they create a massive consequence outside the solid. We're talking about the stuff powering the macroscopic tech we rely on every single day. From data storage in our hard drives to medical imaging and MRI machines. Okay, moving on, let's apply this to the whole concept in materials. Once again, do not just memorize a label. Look at the internal behavior. A hole is essentially a microscopic atomic vacancy, an empty space that acts as a positive charge carrier. That invisible microscopic game of musical chairs actually has a massive real-world impact. It's the physical engine that powers modern tech, like solar cells, smartphone processors, and LED lights. It's all about cause and effect. Let's test this logic out on crystal structures and coordination number. If you just define it as the number of nearest neighbors, well, you've fallen right into the half-answer trap because you haven't explained the physics. Instead, lean on the framework. Link that microscopic atomic packing arrangement directly to its impact on bonding strength. That invisible packing determines macroscopic consequences like heat tolerance, which is literally what stops a jet engine turbine blade from melting under immense stress. Pretty cool, right? Even when we get into highly complex medical physics topics like X-ray production, this step-by-step logic is completely your best friend. Top examiner reports consistently warn that candidates love to confuse cause and effect, so you have to track the sequence precisely. Start with the electron beam bombardment, that's your cause, and trace it right through to the metal target's specific macroscopic emission. Clear, step-by-step causal logic is exactly what unlocks those top marks. All right, we've covered a ton of ground, so now it's actually your turn. I want you to pause this explainer right now. Take 10 seconds and visualize the causal chain from the inside out. Using our framework, exactly how does a dielectric material's internal response make it absolutely crucial for building capacitors? Think about what happens microscopically and what it achieves macroscopically. Go ahead, hit pause. Okay, let's see how you did. Here is the big reveal. Let's read this together. The solid becomes internally polarized. That internal rearrangement changes how the electric field behaves inside the material, allowing the capacitor to store more electrical energy without permitting conduction. That right there is a perfect exam-ready response. Notice how seamlessly it bridges the microscopic cause, that internal rearrangement, with the macroscopic consequence of storing energy without letting current flow.
I highly recommend you take a screenshot of this right now. These 4 prompts, they are basically your ultimate cheat code for exam success. Whenever you study a solid-state mechanism, run it through this exact checklist. Number 1, what is it? That's your basic definition. 2, what changes inside? That's the microscopic cause. 3, what is observed outside? That's your macroscopic consequence. And 4, where does it matter? The real-world application. If you can speak through these 4 anchors, you can flawlessly answer almost any question they throw at you. So before you jump into your next revision topic, I've got one final challenge for you. Can you explain the dielectric effect out loud right now using only those 4 memory prompts we just talked about? If you can confidently track that invisible, microscopic world all the way up to a piece of everyday technology, well, you aren't just memorizing physics anymore. You're mastering it. So what invisible mechanism are you going to decode next?